Amid the sheer cliffs of western Norway, a massive bridge stretches across the fjord. This is the Hardanger Bridge, a structure with a main span measuring 1,310 meters, placing it among the longest span suspension bridges in the world. Construction began in 2009 with a total investment of more than 2 billion Norwegian kroner. The project not only replaced the former ferry route, but also significantly shortened the journey between the two sides of Hardangerfjord, creating a faster connection through a region divided by high mountains and deep fjords. But how were engineers able to build such a massive bridge amid deep waters, sheer cliffs, and rapidly changing weather? In this video, join Mandarin Tech as we explore how Norway built the Hardanger Bridge in one of Europe's most challenging landscapes. Hardanger Bridge is located on National Road 13, spanning Fjord and connecting Brevik with Brims. Before the bridge was built, people and vehicles traveling across the area had to rely on ferries, leaving journeys vulnerable to waiting times and weather conditions on the fjord. The entire bridge is 1,380 meters long, with 2 traffic lanes and a separate path for pedestrians and cyclists. The bridge deck is suspended between 2 concrete towers approximately 200 meters high, while the 55-meter navigation clearance below still allows large vessels to pass through the fjord. However, Hardanger Bridge is not a standalone structure. Both ends of the bridge run almost directly into the surrounding cliffs, forcing engineers to connect it with approximately 2,675 meters of tunnels and 800 meters of new road. Instead of building a route around the rugged terrain, Norway created an integrated system of suspension bridge, tunnels, and interchanges carved deep into the rock. This distinctive terrain turned Hardanger Bridge into a complex project, where the work of building the bridge had to begin inside the mountains. In the Vallavik area, a massive rock mountain blocked the access route to the bridge. Engineers drilled through the rock, creating a tunnel system directly connected to the bridge. On the rock surface, drilling machines created dozens of deep holes in a precisely calculated pattern. Explosives were inserted into each hole, after which the entire area was sealed off. When detonated, the rock face ahead was broken into smaller fragments, but the explosive force had to be tightly controlled to avoid weakening the remaining mountain. After each blast, excavators and trucks moved in to remove the rubble, gradually extending the tunnel. Eventually, the construction team created a breakthrough towards Hardangerfjord. The moment light poured into the tunnel marked the opening of the route through the mountain, creating access to the bridgehead construction site. Tunneling was carried out on both sides of the fjord. Both tunnels were built with roundabouts inside. Part of the natural rock was retained to form the central island of each roundabout. At the Vallavik tunnel, the 2 excavation headings eventually met, marking the moment the tunnel was fully opened. Only then could heavy equipment, materials, and workers move closer to the fjord, preparing for the next crucial phase. Parallel with the tunnel excavation, work also began on creating the foundation pits for the bridge tower footings. Concrete pouring continued without interruption for 50 hours, forming 4 tower footings, each using approximately 900 cubic meters of reinforced concrete. Once the foundations had reached sufficient strength, the 2 bridge towers were constructed section by section using climbing formwork. Workers installed the reinforcing steel, positioned the embedded components, and checked the dimensions. Concrete was then pumped into the formwork, compacted by vibration, and left to harden. When the concrete had reached sufficient strength, the entire formwork system was raised. A new section approximately 4 meters high was then constructed on top of the completed section. The cycle of installing reinforcement, pouring concrete, and raising the formwork was repeated continuously, bringing the tower legs higher step by step. When the towers reached their design height, cross beams were constructed between the 2 tower legs. These beams locked the 2 concrete columns together, helping them resist lateral forces from the cables and wind. To construct the main cables, the team first had to create a pathway through the air. Small guide wires were pulled from one shore to the other. These provided the foundation for installing temporary cables and catwalks for the workers. The construction team then formed the main cables directly above the fjord, using thousands of individual steel wires. A specialized cable spinning device continuously traveled back and forth between the two shores. On each journey, it carried 8 galvanized steel wires divided into 4 smaller bundles. Once all 19 bundles had been installed, a compacting machine moved along the cable, compressing them into a strong circular shape. Steel cable bands were then installed at predetermined points along the cable. From each band, a suspender was lowered. These suspenders varied in length, forming the connection between the main cable and the bridge deck. Their lower ends were left ready for the steel deck sections to be lifted from the fjord. While the bridge towers and main cables were being constructed in Norway, the steel box girder sections of the bridge deck were manufactured overseas. Large steel plates were cut, bent, and welded into hollow structures, with internal stiffening ribs added to limit deformation under load. After fabrication, the welds were inspected using non-destructive testing methods to detect cracks, voids, or hidden defects within the metal. With a total weight of approximately 7,850 tons, the completed sections were then loaded onto ships and transported to Hardangerfjord. In September 2012, the first sections arrived at the construction site. The transport vessel moved into position beneath the bridge. Mooring systems and support vessels kept it stable against wind, waves, and currents. Lifting cables from the specialized hoisting system were lowered and connected to reinforced lifting points on the girder section. Once all connections had been inspected, the lifting operation began. The steel sections slowly rose from the deck of the vessel and continued upward until it reached the elevation of the bridge deck. As it approached the suspenders, the lifting speed was reduced so that the crew above could begin aligning it. The ends of the suspenders were connected to the steel girder. Temporary support structures held the section steady and limited movement while workers brought it close to the previously installed section. Section by section, the girders were lifted, aligned, and secured. The gap between the two shores gradually disappeared beneath a continuous ribbon of steel. Eventually, the two halves of the bridge deck approached each other at the center. When the final steel edges met, the Hardanger Bridge deck officially became a continuous structure connecting the two sides of the fjord. After the steel structure was closed, the Hardanger Bridge entered the finishing stage. The road surface, railings, median barriers, lighting system, and road signs were installed one by one. At the same time, the protective coating and the entire steel structure were carefully inspected to ensure resistance to strong winds, cold rain, and salty air from the fjord. Before opening, the bridge underwent rigorous load testing. Convoys of heavy trucks were positioned at predetermined locations to measure the deflection, vibration, and response of the entire structure. For a suspension bridge, the goal is not to eliminate movement completely, but to ensure that all deformation remains within safe limits. When it entered service in 2013, the Hardanger Bridge replaced the former ferry route, significantly reduced travel time between the two shores, and created a more reliable connection through the mountainous terrain and deep fjords of western Norway. When the Hardanger Bridge entered service, the greatest change was not found in its steel structure or massive towers, but in the way people traveled across the Hardangerfjord region. The ferry route that once connected the two shores was replaced by a road link that operates continuously. Residents no longer had to wait at the terminal or worry about their journeys being interrupted by unfavorable weather. The bridge also helped connect small communities scattered between the mountains and fjords into a more unified transportation network. Goods could be transported more quickly and reliably, while residents gained easier access to workplaces and services on the opposite side of the fjord. For tourism, the Hardanger Bridge created a new landmark along journeys through the Hardanger region. The structure does not obscure the landscape, but has become part of it. Its two towers rise between the Rocky Mountains, while the slender bridge deck stretches across the water, creating a striking contrast between untouched nature and modern engineering. The bridge is therefore more than a transportation structure. It stands as proof of engineering's ability to adapt to nature, a place where humans did not remove the obstacle, but found a way to connect everything through those very limitations. While the Hardanger Bridge holds the record for the longest suspension bridge span in Norway, the Hålogaland Bridge stands out as an engineering marvel amid the harsh, frozen landscape of the far north. Located deep inside the Arctic region in northern Norway, Narvik is not only a cold industrial city, but also an important transportation hub. To reach destinations farther north, vehicles once had to travel along a dangerous winding road stretching beside a fjord more than 200 kilometers long, a route frequently affected by landslides and the freezing conditions of winter. With a total investment of $332 million United States dollars, the Hålogaland Suspension Bridge project reduced the distance from Narvik to the north to just 18 kilometers and cut travel time down to only 20 minutes. The bridge has a total length of 1,533 meters, a main span of 1,145 meters, and two A-shaped suspension towers rising nearly 200 meters from their bases. Construction began in 2013, was built by the Chinese company Sichuan Road and Bridge Group, and was completed in 2018, marking a major international collaboration. The Hålogaland Bridge is not just a local bridge in Norway. It is also an important link in the transportation network connecting the far north of Europe. The tunneling and tower construction processes for the Hålogaland Bridge were carried out in much the same way as those used for the Hardanger Bridge. After the two A-shaped towers were standing firmly in place, the space between the two sides of the fjord was still nothing more than a gigantic empty gap. Before the bridge deck could be installed, engineers first had to create the most important load-bearing structure of the entire project, the main suspension cable system. The first step was to bring a guide cable across to the northern side. This was the very first line connecting the two sides of the fjord, serving as the pathfinder for the entire cable installation system that followed. Once the first guide cable had been secured, the construction team began pulling larger steel cable bundles across the pulley system mounted on top of the towers. Each bundle consisted of hundreds of prefabricated high-strength steel wires. These bundles were gradually pulled from one side of the bridge to the other, passing over the cable saddles at the top of the towers before being anchored into massive rock anchor blocks at both ends. After enough cable bundles had been pulled into place, they were compacted together to form two gigantic main cables. Engineers then continued aligning the cables, compressing the cable cross-sections, installing cable clamps, and preparing attachment points for the vertical suspenders that would later hold the bridge deck. At that point, when viewed from a distance, the bridge appeared as two giant curved steel lines stretching across the fjord, connecting the A-shaped towers like a massive bow suspended between the mountains and the sea. After the two main cables had been stretched across the fjord, the project entered one of its most critical phases, installing the bridge deck. For Hålogaland Bridge, the deck was not cast as a single concrete structure on site. Instead, the engineers used prefabricated steel box girder segments. The steel segments were manufactured in China and then transported by ship to the Narvik area. Each segment was extremely large and weighed hundreds of tons. From below the fjord, the steel segments were placed on barges or specialized vessels. The construction team's task was to lift each segment from the water into its exact position, keep it stable, and then connect it to the hanger cables and the previously installed segments. The segments were lifted slowly. Meter by meter, the massive steel structures rose from the water and moved closer to the suspension system above. Workers high above checked the alignment. Engineers below monitored the loads inside the cables. Once a segment reached its design position, it was attached to the vertical hanger cables suspended from the main cables. Temporary connections were then secured to stabilize the structure. Gradually, the enormous gap between the two sides of the fjord began to close. After many months of installation carried out with centimeter-level precision, Hålogaland Bridge finally began to reveal the full shape of a gigantic suspension bridge spanning across the Norwegian fjord. After the final steel girder segment was installed into position, the Hålogaland Bridge entered its final stage of completion and inspection. Engineers carefully checked the steel structure, anti-corrosion coatings, and drainage systems to ensure that the bridge could withstand years of freezing winds, snowstorms, and salty air from the Norwegian fjord. Before opening to traffic, the bridge also underwent strict load testing. Heavy trucks were positioned on the bridge according to pre-calculated arrangements in order to measure deflection, vibration, and the structural response of the entire system. For a suspension bridge, the goal was not to eliminate movement completely, but to ensure that all motion remained within safe limits. Once operational, the Hålogaland Bridge made travel around the fjord faster, safer, and less dependent on the older roads that were vulnerable to landslides during Arctic winters. At the same time, the bridge also created an important transportation route for cargo, tourism, and port-related industries in northern Norway. From Hardangerfjord in the west to the cold waters of the north, the Hardanger Bridge and the Hålogaland Bridge show how Norway has transformed deep fjords, rocky mountains, and harsh climates into seamless transportation links. One holds the record for the longest suspension bridge span in the country, while the other rises as an engineering marvel near the Arctic Circle. They have not only shortened travel times, but also proved that engineering does not always need to overpower or remove nature's obstacles. Sometimes, it simply needs to find a way across them. Which bridge do you find more impressive? Hardanger or Hålogaland? Leave your thoughts in the comments, hit the like button, and follow Mandarin Tech to continue exploring the world's greatest engineering achievements.